Tipo. Này. Thì cái hành khinh.
ชื่อตัวเองยังไงนะ
Can you hear me?
Pega-san, can you hear me?
I can hear you. Can you hear me, Takashi-san? I can hear you, Takashi-san. Can you hear me?
Okay, thank you very much.
Organization that use this technology.
Sorry, Pega-san, can you speak again?
Can you hear me now?
Yes, I can hear you, but the volume is a little bit small.
Oh, really? How about now? Can you hear me?
Yes, I can hear you. I will check
Is it
the
better?
setting from our side.
How about now, Takashi-san? Still, the voice is small?
Yes, but I will set the speaker on this Jackson's booth. Just a moment.
Okay.
音しないですか？
力出すの。
昨日、フィジカルで押すしかないけど、自分で押せない。
見えないね。はい。 はい。
高橋さん、今、画面は見えます。
Yes, yes, I can see your full screen. Pegasan, can you speak again?
Can you hear me well?
Yeah, okay, it's good. Thank you.
Great.
Also, can you hear me as well? Hello?
Hi, we
Yes,
can hear
I can.
Okay, good.
Pegasan, can you hear me?
Yes, I can hear you, Takashi-san.
Okay.
わかりました。じゃあ、
あ、いいです。背景がいきなりレステクになっちゃう。それよくない。そのまま直接パスなくてもいいですけど。とりあえずオフにしてくれれば。はい。失礼しました。Hello, Pegasan.
Good afternoon, Sobu-san. Can you hear me? We can
Yes.
see you and we can hear you.
Yeah, clearly I can hear you. On the on-site is how many people is in here? There.
I will share. I will show the room with my laptop camera.
ต้องหาตรงที่ไม่มีไฟป่ะ
สวัสดีครับ
มันเป็นเสาไฟมีภาพแบบตรงไม่มีไฟ
はい、大丈夫。はい。So
Sobu-san, there are
yes.
20 people in the room.
Yeah, okay. I can see crew one and I don't know others. It's the person here, including. You know the crew ones. Yesterday I got this one. Thank you very much. This is the.
Okay, should we start, everyone? Okay, hello everyone. I am Dr. Wisawa from GISDA. First of all, I would like to welcome around 20 GISDA researchers here on site and more than 100 people online joining us from across the country today. Overall, everyone should be in the expertise in geoinformatics, I think. As you all know, we have the training course collaborated with Japan Aerospace Exploration Agency or JAXA, GISDA, and RESTEC today. The title we have for online session is Application of ALOS2 Level 2.2 ScanSat data on forest and surface water mapping for end user. So this session for the online, we aiming for end user. We are showing them the web mapping for the end user. And this topic will be lecturing by Dr. Pekka Hashemwal. She is an Earth observation and geospatial application expert from the Remote Sensing Technology Center of Japan, or RESTEC. Before we move into her, I would like to introduce Dr. Subue Shinichi. He is Deputy Chief Officer of Earth Observation Application and ALOS2 Mission Manager from JAXA to give you the opening session remark for 10 minutes. He is joining us online from Thailand Space Week. Okay, Dr. Subue.
Thank you very much, Popop. Komchu Shin Sobue from JAXA. And as MC already mentioned, I'm in the Bangkok, but unfortunately, I'm in the Thai Space Week booth of the JAXA. Therefore, I cannot join physically in this office. But I'm very happy to have this opportunity to make a brief opening remark of this occasion. And I'm very happy and I'm very appreciative in the Dr. Kuruwan and the other staff to have the opportunity to have this training course by the GISTA with JAXA RESTEC. And today is based on the request from the GISTA. Ms. Pega, Dr. Pega will be sharing the information how to using the Google ALOS2 data with Google Earth Engine for the forest cover and also the land surface water detection. So it's very, I strongly believe it's very important for the Thai to know the such kind of technology. And I also looking forward to you in the Thai people by research to improving Pega's application and to have the more good result in the Thai. And I'm looking forward to coming over to Thai again in the next year and to see the status of how improving in the how research collaboration should be going. So thank you very much. And I would like to hand over to Pega. So see you next time or tomorrow in person.
Thank you, Sobue-san. In time, I will share my screen and I will. The mic is closed. Is it okay now?
Yeah. Sound is clear. Pega.
I will share my screen and. So good afternoon, ladies and gentlemen. Thank you, Sobue-san, and thank you for GISTA for introducing and having a opening remark. Thank you for all of you giving your valuable time to join to this session. We have about 20 people in the room, and I see at least 200 people online. Thank you for your participation. I hope that by the end of this session, we can share our knowledge, not only from our side, but also from your side, your expertise from different fields. And I hope that by the end of today, we can build up a very good network so that we can make this platform and network together for future work and opportunities. And my name is Pega from Remote Sensing Technology Center of Japan, and I will be talking with you for next about 1 hour. So without further ado, I would like to go into a very brief introduction about the outline of today's first session. Basically, in this session, at the beginning, I will give you a very small introduction that why we have such kind of plan, why JAXA is trying to initiate this engagement of the end user into application of the Earth science, Earth's observation. And after that, we go a little bit into the background of the SAR remote sensing. It would be a little bit difficult for me to discuss that because I see so many engineer and officer from GISTA with the high expertise on the matter. But since we have other people from different background, I would like to just set a very simple background on this background of SAR. And then we move to a little bit of the L-band SAR on the forestry and surface water. And after that, I briefly introduced two similar web-based applications, which has been developed based on ALOS2 data on Google Earth Engine, and we briefly introduce how to work with those, and we hope that by the end of session we can have a very interactive discussion, and based on that discussion we can go for the next level of the application and improve it and bring that application really into the practice for the end user. So without further ado, let me discuss this diagram that is very interesting to me. I was looking into the fact that how we can bring the value of Earth observation data into the action, not only JAXA, I believe GISA and other space agency. The ultimate goal and I would say dream is that to bring the data that they produce into the actual planning, actual action, policy makings. But to bring the data onto into such level, there is different steps. It was really interesting for me to come across this kind of diagram. It made it more clear for me that how many steps we need to take and how many parties needs to be engaged for such kind of basically ideal situation. And at the basement, when you see we have this Earth's observation data or the surveys or the fields data collector, that they basically produce the data. But the data itself is only data, and there is no powering to it unless we transfer data to the information. And that's basically the job of the expert from, for example, remote sensing or the other area, which take the data, for example, provide some sort of maps and things like that. And when, for example, Earth's observation data transfer to some sort of map, it's easier for those people who are not directly engaged to Earth's observation to interpret it and understand that. But the still map itself would not be enough to take action based on, because we need to have some wisdom and knowledge based on those maps. For example, if it's the map about forest cover, itself cannot be really informative, and we need to have, for example, officer from the forestries who have the knowledge of the field and who knows the background, who knows the actions, and who know who have some perspective about future. We need them to interpret those maps. And based on that interpretation, now we can expect that, okay, there would be some policy briefing, some white paper, so that based on that, the government can initiate and can start making some policy. But to take those steps and get to that dream situation, there is always different strategy and different task that space agency does. One of them is to improve the accessibility, meaning that if it's GISTA, if it's JAXA or other space agency, they kindly offer the data to the public without any fee or without any expenses. So that's the first step to bringing the power of the Earth's observation into the action. And this today workshop is part of same approach, because we are going to introduce how ALOS2 data is now publicly available in the Google Earth Engine and other platforms. So this is one of the steps or strategy that the space agencies usually take. Along with the accessibility, always this collaboration makes a huge impact in terms of improving and working with different application, if it's forest application, if it's the surface water application, always this collaboration makes those application more in-depth and more reliable. And after that, based on those information, we have this responsibility to increase the awareness to the public. Today's session also is part of that strategy, that we try to share our information with the large group of audience and range of the end user, so that by the end of the day, we hopefully get to the point that we know what is some of the potential of the Earth's observation, and that would set the ground for future activity. So with such a background, I would like to just give you an overview that today is part of a longer time program that JAXA is basically planning, and that is on the March of this year, we had another public session that we introduced the application of the ALOS2 data on Google Earth Engine. And on that session, after the session, we had this questionnaire among the participants, and then we asked them, what kind of application do you want to use ALOS data for? And the result was interesting because in the Thailand side, so many of the people who answered the questions, they emphasized on the importance of the change detection, specifically on the field of forestry and surface water, basically change detection. And that's why we thought that this is a good ground to start all this activity. But we cannot deny that some of these cloud computing platform that we have the data available on, they are not easy platform to work with, because you need to have certain level of expertise or coding knowledge to access them, to use the data. So that was the very big obstacle for that is actually very big obstacle for end user with no knowledge of the remote sensing or coding to use that data. So we thought that, okay, let's try to remove that obstacle as much as it's possible. And we come up with the idea of working with GISTA and other space agency and also end user to make it possible for user to get the advantage of the data without working with code, only with some interaction with the user interface. That was when we had this idea of the web-based application for two application of the forest and surface water change detection. And we hope that with this kind of session, we can share our knowledge, and hopefully by the end of this fiscal year, which would be March 2024, we can discuss and exchange our mind and improve this application. The application itself at the moment take very simple methodology and very simple algorithm, but we hope that by your comment and your expertise and sharing our knowledge, we can level up this kind of activity, and we come to the point that we really introduce this kind of application to the end user for real actions and sensible action, basically. So that was a very brief background on the why we have such kind of session, and what by the end of the day, what we really would like to have. And with that, I would like to go to the rest of presentation, which is more on the remote sensing side, and later more specifically about the SAR system. Again, it is not easy work for me, because here I have at least 20 of my colleagues from GISTA, and they all, in daily basis, they are engaged into the analysis of the satellites imagery. So it's not easy job, but I hope I can share at least some new information with those who are not familiar with the remote sensing today. So basically, as a very basic knowledge of remote sensing for those people who are not familiar, we do have two different remote sensing systems. One is the optical system, and the other one is a synthetic aperture radar system. That's how the word of SAR comes. synthetic aperture radar. So let me dive more into how these two systems are different from each other. So we have this at the beginning, we have this optical system that you can imagine this system as exactly working similar to our vision. So in the presence of the light, our eyes can receive the reflection of the light from the Earth's surface and objects, and that's how our vision works. But imagine if in this room we close this curtain and we stop any source of light, there would be no any more information from our surrounding. That's how exactly optical systems are also work. On the left-hand side, I put a example from the optical sensor, and that example was taken from the Mekong Delta in Vietnam. And as you can see the Delta region very clearly, but also you can see the huge effect of the cloud contamination. And if you look into the image, you can guess that probably we lose at least in this picture, in this image, we lose at least 30% of our information we could potentially get from the area. That's because of the cloud cover. And that issue is really challenging for us as the Southeast Asia community, because all around the year we have this cloud contamination issue. And in the typhoon season, which we need the observation the most, we get the least observation due to based on the optical sensor because of the cloud contamination. So to compensate this issue, scientists came with another idea of SAR system. This system sent the sensor in this system, the sensor send the radiation into the Earth's surface and receive back or the back scattering from the same radiation. Why is this important? The reason is that those radiation can penetrate into the clouds. So the cloud would be very transparent for the sensor, and you won't have any issue with the cloud coverage. That's really important and a good achievement for us. But the issue with those SAR images are they are usually very difficult to interpret, especially if you don't have expertise or experience on the SAR. They are not visually really understandable. Even for the expert, without having the knowledge from the field, it's really difficult to interpret it. On the right-hand side, I put you an example from ALUS2 data on the same date, same region. So you can see that we don't have any more the issue of the cloud coverage, but the image is rather difficult to interpret if you don't have any knowledge from the region. So I basically already discussed this slide. This is about the pro and cons of each of these system and data. And just I refer you to, again, to those example imagery that one taken on the left-hand side with the optical sensor and right-hand side with the SAR sensor. You see that the interpretation of the SAR, it's really difficult. But we don't have any issue with the cloud here. So that's the message that we get from this slide. When it comes to the SAR, from now on, I would like to move a little bit into SAR specifically, because that's how that's basically the ultimate goal, that we get to know the potential of the L-band SAR specifically in this lecture. So there are some characteristics for the SAR system that are really important for us to know before selecting the data with regard to our application that we have. One of those is the SAR wavelength. So as I mentioned earlier, basically in opposite side of the optical sensor, SAR sensor usually have one specific wavelength that they work on. And you can imagine that like a very specific set of glass that you put on your eyes, and everything based on the wavelength that you select only you see specific things on the Earth's surface, and anything else would be transparent to your eyes. So that's why it's really important. How do you select the wavelength based on the application? And as a rule of thumb, if you want to remember that, you can imagine you can see the Earth's surface, those objects on the Earth's surface, which their size is equal or at least equal or bigger than the size of the wavelength. That's how you see. If it's smaller, you basically don't see those feature on the Earth's surface. Here on the left hand, in the right hand side, I brought you 2 examples from 2 wavelengths, and they are the C-band and L-band. C-band has a very short wavelength of 6 centimeter, and L-band has a higher wavelength of about 24-25 centimeter. As the wavelength gets bigger, there would be more power of the penetration. So when you have a higher degree of the wavelength, you could basically expect your signal to penetrate into more into the median that you have on the Earth's surface. So if you look into the right-hand side figure, you see that the first example is the rubber plantation in Vietnam. And at the time that we use C-band with 6 centimeter, if your goal is to differentiate the different status of the plantation, basically C-band with 6 centimeter cannot give you much of information. The reason is that the C-band will stay on the top of, penetrate a little bit into the canopy, but cannot really go in deep because the wavelength. But at the same region, when you use the observation with the L-band, because the wavelength is quite higher, the wavelength have this chance to penetrate into the canopy, interact with the trunk of the tree, the ground, and will give you more information. That's why in the false color composition in the right-hand side with the L-band, you see more information if your goal is to see the different stage or different status of the plantation. The next example is again using the C-band and the L-band, and this time it's based on the example is based on the inundated vegetation in I guess it's in Brazil. And you see that when it comes to the inundated vegetation, C-band, although there is some research showing a promising application, but there is, in compared to L-band, there is a less chance for C-band to penetrate and interact with the water beneath the vegetation and come back to the sensor with more information. So you see that in the left-hand side figure for the C-band, you really don't get any information on the extent of the inundated vegetation, whereas you see in the L-band, you get a clear image. That's because the radiation can penetrate into the canopy, can interact with the water beneath the canopy, and then return back to the sensor, so you get more information. So the whole message of this slide is to give you this idea that how the wavelength is important with regard to your application. And the message that you can take from this slide is to remember that as much as the wavelength is bigger, there is more chance to penetrate into canopy. So if your application is forest, or if you deal with the inundated area under the canopy of forest or vegetation, L-band is one of the best choices that you have. And so another thing that is very interesting, and I thought it would be informative, is a backscattering mechanism that we see in the SAR. And that's really helpful when it comes to the interpretation of your image. That's why I brought some example for you here. The first mechanism that we have is the surface, basically surface scattering. And if you see that area highlighted with the yellow circle, you see that we see a very, very dark pixel over there. The reason is that this surface, from the shape, we can visually interpret that this should be some sort of river, right? But if we don't have that shape, what we can interpret is that the surface, whatever we have on the surface, has very smooth structure, so that it acts exactly like a mirror. And if you imagine the radiation comes from the left, it hit the surface and go in the opposite direction of the sensor. So eventually you don't get any backscattering from that surface. That's why your pixel look like very dark and the backscattering is really small. So just remember that when you have a very dark pixel, in the case of this example, it's a very smooth surface that is scattering the radiation into the opposite side of the sensor. Now I want to bring your attention to the other part of image, and you see maybe on the screen it's not really clear, but you see here we have again a set of dark pixels, but they are not as dark as the first example, and the backscattering value is not as low as the first example. With the background and explanation that we had from the beginnings, you can imagine that whatever we have on the surface has a little bit of roughness. So when we have the roughness, that roughness scatter the radiation in different direction equally, and there is some small portion that come back to the sensor. That's why still you get a dark pixel, but not as dark as the first example. And as the roughness of the surface increase, the backscattering also, you get more backscattering. So the backscattering more also increase, and you get basically lighter color of the pixel. The next example, which is a dominant case in this image, is another basically mechanism in the backscattering, which is volume scattering. That's the case that when you have a volume into your Earth surface, like a canopy of the tree, the radiation would penetrate into the canopy and interact and go basically interact all over the canopy and then return back to the sensor. That's basically volume scattering, and that is dominant type of scattering in the forest. So when you look into the forest from the SAR imagery, you see a dominant impact of volume scattering. Then we have another type of interesting backscattering mechanism, which we call it double bounce scattering. And this is the case when we have two relatively smooth surfaces perpendicular to each other, and the radiation hit the first one, and then the reflection hit the next one, and then go back to the sensor. So you have this double bounce backscattering, and this result into very, very high backscattering and a very bright pixel, as you can see. And this is a dominant case in the case of urban area. You see, because the structure of the building and Earth surface make that perpendicular space, and you would see a great double bounce impact. Beside of this urban area, you see the same impact of double bounce in the inundated vegetation as well. So in the inundated vegetation, the trunk of the tree and the water beneath, they make that surface, and you see a pronounced impact of double bounce. So these are really important because these help you to interpret your pixel value and interpret what you see, because unlike optical sensor, it's not familiar feature with our eyes. So this is for the backscattering mechanism. And the last character of the SAR basically is the polarization. Again, polarization is something that very important to note, before selecting the data, because that would also impact what you can see and what you cannot see. This example and the feature, I forgot to add the reference here, unfortunately, but this is a very famous feature that whenever you search for the SAR course, you would definitely see this feature. But you can imagine polarization as the one string in your hand. And if you shake this string up and down, that would make a vertical wavelength, the vertical basically radiation. And if you shake it like a left to right, that would bring the provide you the polarization in the horizontal aspect. So this is important because the polarization would define how much your radiation has the power to penetrate into the feature. So it's really, again, important to note to that. From now on, you may hear me saying HH, HV, VV, VH, something like this. These are all referred to the polarization, different combination. We have 4 combination HH, as you can see. I'm not going to read all of them, but I just give you 1 or 2 as an example. So when we have, or we say HH band or HH polarization, we refer to the combination of the horizontal transmit and horizontal receive, meaning that the radiation is going to the surface with the horizontal horizontal polarization and receive back in the same way. And then we have the HV, VH, VV polarization. These are really important because you can see they impact how the radiation can penetrate. And as a rule of thumb, you can remember that HH is one of the powerful polarization that can penetrate into the canopy. And HV actually is one of the best polarization for the open water detection, and also if you have some sort of vegetation, it's also very powerful because it has the impact of the volume scattering inside. Now that you have this overview generally about the SAR system, SAR characteristic, I would like to introduce ALOS 2. ALOS 2 is a mission, and the name stands for Advanced Land Observation Satellites 2, manufactured and operate and is still operating by JAXA. The sensor on board of these satellites is L-band SAR sensor, meaning that the sensor sends the signal in the wavelength of about 24 centimeter into the Earth's surface. I already discussed how the L-band SAR can be useful, but there are more to that application, and there is some of these applications that initially designed for the ALOS 2 project and mission. One of them is about disaster monitoring for the damaged area. You can assess the volcanic activity, land subsidence, land uplift. Also for flooding, there is a good potential, as I mentioned, because the radiation has a power of the penetration. Also agriculture, which is a very important field of activity for the SAR. Also for the forest management, and the application that might be less covered is about ice and oil spill detection. So these are the applications that potentially we can use the L-band SAR into it. But today specifically we work on the we discuss about the forestry and flooding or surface water, but there is more to into that. So when we were waiting for the people to gather into the Zoom, and we just reviewing some names of agencies, Gista colleagues introduced me that there is a huge range of people from different backgrounds. Some of them are the statistician from the forestries organization, and some of them from the water management agencies. So it's good. I thought it's good to cover this more specifically and discuss them, how L-band SAR would look like in both cases. So I don't discuss, as mentioned in the top, I don't discuss really the importance of why it's important to use the L-band SAR in this application, because when we have you already here, it means that you know there is some potential. So I don't discuss that, but I rather discuss some example how you can interpret your image, or how you can expect to see your image in different cases. So in the case of the first example is a forestry example, forest cover example. When you look into the, this is a very nice diagram showing different potential type of the backscattering mechanism under the forest. The major backscattering, of course, it's really depend on the status of your tree and the type of the forest. Everything would be really impactful, but usually the pronounced impact come from the volume scattering. So the number that would be number 4 in this diagram. There would be other type of backscattering mechanism, but the majority that we see is from the on the forest canopy of forest would be volume scattering. And that for that, I bring your attention to the kind of green circle example in both HH and HV polarization. Unfortunately, I guess on the screen it's not that much visible, but I hope Zoom people on Zoom can understand the difference in the color. But on the HV image, we have brighter pixels in compared to HH pixel over the forest canopy. That's because HV polarization usually have the impact of the volume scattering, and that's why basically when it comes to the forest canopy assessment, we really we usually suggest the use of HV. And you see there is the backscattering in HH a little bit less than HV in the case of forest canopy. But when we have in the next plot highlighted with orange color, when we have the forested area, when we have a clear canopy, again in the screen it might not be really visible, but you see a very you see the impact of the double bounce scattering in HH quite a high. So I would say, as a comment to take from this slide, I would say depending on the situation of your forest, both HH and HV would impact and would be helpful depending what you want to see. If it's the deforestation, there would be a good chance that you get the information from HH as well, good information from HH. And the other example is basically related to surface water. Surface water, probably if you look into the very left-hand side image, usually surface water is more confusing because it shows two different backscattering mechanisms depending on the situation. If you have a very open, in the case of open water, because you have the almost smooth surface, you get a very little backscattering and your pixel is really dark. But when you have the inundated area on the surface, due to the impact of the double bounce, you get a very bright pixel. So if you are trying to feed your training data into the algorithm to classify the inundated area, you need to think about excluding or somehow differentiating this opposite side of the spectrum, open water and the inundated water. And about the polarization, you can see that in the case of inundated area, again, because of double bounce scattering mechanism, HH is one of the best polarization that you can use. If you compare HH, HV, and VV, HV basically doesn't show that much information about your inundated vegetation, but in the case of HH, you have a better view on the changes. And in the case of open water, HV usually is the best polarization we suggest for the observation. So with that background, I hope by this part of the presentation, you get some idea about how you can use potentially SAR and specifically L-band SAR in different applications. And if you come across some sort of data from ALOS2, I hope that you can use this information to interpret your image easier. But I would like, from now on, I would like to move to this last part of the presentation, which is a discussion about, or I would rather say, introduction of the web-based application that we have based on ALOS2 data and Google Earth Engine. I start this with a very brief introduction of the Google Earth Engine, and after that I would move to introducing both applications. So Google Earth Engine, I'm pretty sure that those people who are in some level engaged with the remote sensing and Earth observation data, you definitely have come across the name of the Google Earth Engine. But for those who haven't, Google Earth Engine is basically a cloud computing platform which has a huge archive of the Earth's observation data and geospatial data and any data regarding to geospatial information of the Earth's surface, as long as it's in the public domain. And from the time that Google Earth Engine and the other similar cloud computing platform came to existence, they have been basically transforming the way that we work with data quite drastically. And within these last 5-10 years, the remote sensing community has been experiencing a great shift from traditional way of processing data to cloud computing platforms. And Google Earth Engine is not the only one, but it's one of the most common way that people use use this cloud computing platform to work with the Earth's observation data. But if you are not from the remote sensing area, I would like to give you just a very short example how the processing of the Earth's observation data looked like before, like 10 years ago, and in compared to now with having the cloud computing platforms. Before emerging of the cloud computing platforms, if you are so, at least in the room, I see so many young faces, so I'm not sure if you remember, but those have a little bit longer experience may remember that before we used to first be connected to the portal of data provider and take the data and download the data from the data provider portal. That required us to have internet connection or some sort of connection, and then storage capacity, because we needed to download the data into our local machine. And then once we download, we always had this issue of the data management, where to store the data, how to manage the data for the later reference and things like that. So that was also required us to have a good capacity for storage system. And then now, if you successfully done with those steps, you needed to do some certain level of pre-processing to make make your data ready for your analysis. And now that you do everything, the pre-processing, you are from now on in the position to start your analysis and then publish your analysis. But with the emerging of the cloud computing platform, luckily so many steps have been removed from this process. Namely, you don't need to really be connected to the specific data provider portal. Majority of the data publicly available now are also available in cloud computing platform. For example, ALOS 2 data is now available. Whole the Landsat archive is available. Sentinel archive is available. So you don't really need to go to different portal. It's easy. And the most important part is you don't need to download the data into your local PC. And that's a huge step, especially for those who are not necessarily work with the Earth observation data in daily basis, because you don't need to have the high performance computer. And on normal computer, it's really difficult to store that huge amount of data when it comes to, for example, country scale analysis or time series analysis. So you don't need to basically in cloud computing platforms download the data. You only import them to your code editor without engaging any processing unit of your computer, and you work with them. And that was huge steps, especially when it comes to the countries with limited resources. For example, my own country, we cannot always have the best performance computer, so it was huge step of the accessibility for us to work with the data. And that's why nowadays Google Earth Engine and cloud computing platforms are getting really famous, and everybody are really excited to learn and talk about them and work with them. But with all those goods, there is some disadvantage as well. One of the biggest disadvantages is that usually these cloud computing platforms, they require some level of the coding expertise. Depending on platform, the language would be different. But in the case of, for example, Google Earth Engine, you would need to know certain level of either JavaScript or Python. And that is a huge obstacle when it comes to non-familiar user. And this is a big disadvantage. To compensate that part of disadvantage, most of these cloud computing platform, I speak only about the Google Earth Engine actually, they come with the user interface, basically module or algorithm as well, so that if you are in the position to share some information with the end user, you can easily make them safe without engaging them into coding and all those technicality, with some simple user interface. And that's how our Google ALOS 2 web-based application came to existence. That's based on the user interface on the Google Earth Engine and ALOS data. So we don't expect to involve the end user into technicality, code, and remote sensing analysis and techniques. We rather get some input from the end user, and that input would be the source for us for some information, and we would generate some results based on that. So I talked a lot about availability of data on Google Earth Engine. I would take a chance here to just introduce and give you a little bit of background about ALOS 2 data archive available on Google Earth Engine. And this is ALOS 2 ScanSAR level 2.2 data. This data, the format of data is very specific format, in basically in accordance with the SEOS Committee of the Earth Observation Satellites. The reason that's the format is important because this commitment or this format ensure that we have removed unnecessary pre-processing step for unfamiliar end user. So if traditionally you would need to take several pre-processing steps, with this level of the data, with this format of the data, some of them already done. So you don't need to be worried about that. So it's basically how we say it's machine ready, readable. Basically, I don't remember exact word, but yeah, machine readability is really high. I don't exactly, sorry, remember the keywords, but anyway, about the data archive specification, at the moment, by the end of October, by this October, we have the data from the beginning of the observation of ALOS to August 2014 up to August 2000 to end of August 2023. And the data latency is about 2 months. So from the time that the observation is made until the time that the data is available on the Google Earth Engine, it's about 2 months. The latency is about is a little bit wide, but basically JAXA is trying to reduce this latency and prepare the data for the more real-time application, near real-time observation. And the special resolution is about 25 meter, which to my knowledge is good enough for some certain level of the forestry studies and surface water detection and such kind of applications. One of the limitations that we have with these data, and I would like to emphasize because probably there would be some question on this, is that due to the level of the pre-processing of these data, and also due to the limitation that we have within the structure of the Google Earth Engine, there is no potential for us to do INSAR analysis, land subsidence, land uplift. Unfortunately, Google Earth Engine doesn't have the capacity of supporting such kind of analysis, and the data level also is not suitable for such kind of analysis. But regardless to that, this data is really powerful for land use and cover change mapping, forest cover change, and importantly, water management in paddy fields, because has the power of the data has a power of penetration into the canopy and interaction with the surface water. Here, this is not really, in some sense, this slide is not really related to the topic, but again, that goes back to the point that to download the ALOS data from Google Earth Engine, you need to have some sort of coding expertise, but we already prepare a user interface for that. So you can refer to the link at the top, access to the user interface, you specify some variable and you download the data into your local machine if you need to do so. So this is basically a bonus kind of a slide, not really related to the whole topic, but this is how you can easily download the data. In this slide, I try to introduce both application. You can access both of them. Both of them are, in terms of the structure, are identical. The only difference is that the one related to forest application use the forest related training data, and the one for the surface water use another set of data sets, but the structure is identical. So you can scan the QR code access, or you can click on the link and get access to the data, to the application. From now on, since the time is running, I try to just introduce the user interface. And then after that, if you have time, I quickly show you the how to work with that. So the panel, we have two different sections for the panel. The first section is the place that you specify a different variable about your observation. And then the second section is the part that you define your training data. So this example specifically is for the forest cover, but the back-end structure is based on the comparison of two classified image. So to do that, you need to define two periods of observation. In the first place, you need to specify that period of observation for before image and after image. It's quite straightforward. The only thing that you need to remember is to follow the format of the input. The year should be in 4 digits, divided with hyphen, months in 2 digit, and day in 2 digit as well. And you can play around with this within the observation period of ALOS 2. After that, you have option to go either with the country-wise assessment or define your area of interest. The country-wise assessment is country. If you click on the country, check on the country option, that would be the shapefile of whole Thailand showing up on your screen. But if you check on the specific region of interest, there would be a set of drawing tool activated for you to draw a specific shape over your area of interest. I'm pretty sure that is very straightforward and nothing complicated about that. And in the last part of the first property section is about some filtering of your SAR data. The first part is the place that you select with how is your orbit path should be, whether you want to look into the images taken when the satellites go up or go down. You can select, or you can keep it as it is to consider both images to improve the frequency of the observation. And the last part is about the speckle filtering, because SAR data basically are very prone to the noise, and you see always this salt pepper effect. And if these are really important for you, with the simple check, you can remove them. But if your time of observation is wide, like yearly basis, probably you don't need to remove them. There would be less. So in the last part, we have the training data preparation. This is a place that we are really hoping for, because this is the part that we hope that we can engage the end user with the expertise of the field to prepare a good quality of the data. So here we have three basically methods of training data, which will be fed into the machine learning algorithm. So the first one is to use the default one. If you check on, there would be a default training data. That default training data in the case of forest application comes from the ALOS 2 forest and non-forest data set. And in the case of the surface water, that come from the global flood data set, again, covering whole Thailand. But the data sets, both of them, the quality, still there is some space to improve. So you can check, and if the quality is not satisfying, you can move to the next option that we have, which is preparing the data set within the application. So if you check that option, there would be one widget or one small window open to you in the display panel. And that's the place that you will be able to take a sample from your image right straight from the Google Earth engine. And there wouldn't be any engagement of another software like QGIS, Google Earth Pro or something like that. So since the interpretation of the SAR data is really difficult, once you click on that option of preparing the data set, another set of imagery, but this time optical imagery, will be added into your display panel. So beneath you would have SAR image, but at the surface and top, you would have Sentinel-2 image. So it's easier to interpret it. But the period of observation is the same period. So you can make sure that this is the same area, same time. I'm looking with different sensor. So once you have that optical sensor, you can start taking points from your web browser, and you activate the pin, or you can take a pixel or basically polygon. if you have a uniform pixels, you can start and taking pixel. The only things that here is important to remind you is that this application for now, because it's just a prototype application, just take 2 classes, not more than that. And the first class is always your target class. So if the application is forest, the first class is always should be taken from the forest, and the second class could be anything other. So that's the only thing that you can remember from this. And the good point about this application is that you can export this training data into your computer, and when you click on download link, a link will appear for you, and you can download the KML file for your data, and then you can work with that in any GIS software as well. And the third one is the place that if you have already prepared a training data elsewhere, you can import it here, but for that you need to already have a Google Earth Engine account. For the rest of this application, even without Google Earth Engine account, you can use, but for here, you need to have the Google Earth Engine account. You need to upload the data into your private asset, make that asset public, and then copy and paste the asset ID here, and then you can run the program. And once you run, for example, this is a case for the country-wise assessment, and you see that when all the processing is finished, on the very left-hand side at the bottom of display, you have some accuracy assessment summary that would tell you how many pixels have been used for training, how many used for testing, how's the accuracy, how's the kappa coefficient. And then on the screen, on the display part, you see the ALOS data, you see the extent of, in this case, a forest cover, and you see the extent of potentially distributed forest as well. Here in the red color, you see, like that example. And this is the extent of forest, and that's basically all of the application. The application for the surface water also work quite similarly. And with that, I would like to basically finish my presentation. And after this, if we have 2-3 minutes, I will show you on my screen how to work with the application. It's a straightforward, but just as a demonstration. But to finish this presentation, I would like to emphasize that one of the ultimate goal of such kind of program is to share our knowledge from our side, the knowledge of Earth's observation and remote sensing, but from your side, the knowledge of forest management, the knowledge of the water surface water management, and such kind of things. We really hope that we can empower our surrounding community and make our network so that we can mutually benefit from this network. You share your expertise with us, we share with you our knowledge, data, and the application that we have. So eventually we hope that this application, accuracy wise, they are not accurate at the moment because this is the prototype stage, and the structure behind this is really simple. So we hope we can work with on that with GISTA engineers and experts to improve that. And we hope that we can, through collaboration with GISTA, we hope that we can have your knowledge on the field through training data collection, and we can empower eventually within 1 or 2 years, empower such kind of applications so that we really can make an impact in our surrounding community. With that, I would like to close the presentation here, and then I move to the, I will stop my sharing and then reshare again once I connected to the application. Just give me a moment, please. So this would be the whole user interface that we have at the moment at the prototype stage of the application. It's pretty simple, nothing complicated, and we also have the basically step by step you say tutorial for the how to work with this, but it's quite straightforward. As the default are already put some date here between 2000 to sorry, just give me a second. Yep, sorry. This is the so as the default, I already set a date for here, and since the country wise it's pretty much clear, I will go for the some specific area. Sorry, I don't have knowledge about the Thailand. Where should I go for the forest? But I think this place might be good. I check the region of interest here and I draw a polygon, and you see it's already is on the layer as my area of interest. For the orbit path, I have this option to select either of ascending or descending, or you can just keep it as it is to take both polarization. Speckle filtering, you can check on, since I have quite a big range of data here, I don't check. And then you can apply and visualize your image here by applying and display the ALOS 2. And you see that on that area, you would see the before and after observation ALOS 2 data. Before, after, before, after. And you could, on the training data preparation, you could go either with the default, or you can prepare the training data or import. I would go with the preparing the training data here. As soon as I check this, you see there would be 2 optical imagery also pop up. I only work with the after image, so let's we have it. So now it's visually much easier to refer to. And now I make first layer of the training data that I want. When you see there is a circle here, it means that the layer is active for sampling. And then I would take some sample from those places that I think they are. Just give me a second. Just I don't take a precise sample here, it's just demonstration. And then I go for the second class. I take the sample from those area that I think there are not forests. And then if you are satisfied with your training data, you can also download that, get the link. And here it would be your KML file here on your machine. You can work with that later. And then once you are done, you push start and the classification will be done. The classification here is based on the random forest with 100 trees. And here you see the number of training data, testing data. Since I have about 39 samples, 30 samples have been taken as training, and the testing 9. The accuracy is about 70%, and kappa coefficient very low and not satisfied. But anyway, this is the whole concept of the work. And we hope we can improve the accuracy, the algorithm, and everything behind, so that we can really bring the power of the ALOS data for the end user. With that, I would like to thank you for your listening, and I would like to finish my presentation here. And probably we can go for the Q&A session if there is any question. I'm not sure if Sobo-san also available on the JAXA booth.
Yes. we can accept the question to Dr. Sobue.
Yes, please give me a minute. I cannot at the moment see the questions. YouTube from YouTube. Do you want to start with the question from YouTube first?
They just would like to know that the resolution of the map that is in the web application of the LS.
25 meter.
Ah,
Yeah.
okay, 25 meters.
Yeah.
Okay, the first one, yeah. And again, about the polarization, what is the best for detect the vegetable?
Vegetable, I would say still HV, but I would rather ask Sobue-san to answer the question. Sobue-san, is there any specific polarization you suggest for the vegetable?
Vegetable. It's very difficult to detecting a vegetable because it's dependent on the vegetable type of the vegetable. Because it's like tree orchard, it might be very difficult. Maybe it's but even in the like strawberry or some of the food, maybe high resolution is better. But since L2 is only the single polarization for the 3 we have to careful to think about what is good to use one single polarization for the 3 what try to using the full polarization, quad polarization for the 6 we have to check it. But unfortunately, I don't have any concrete answer yet.
Thank you so much. Can I ask you to read the question, because for some reason I cannot open the chat box here, so I cannot see the question and read the question. I don't know. I think I play around with the chat box.
Patrapon, you can access the question from the YouTube. Only one question that we have. Only one question.
Okay. And from the Zoom, do we have any question?
Or inside this room, on site, do we have any question here before we have a break?หรือใครอยากถามเป็นภาษาไทยก็ได้นะครับจากผู้เข้าร่วมชมออนไลน์ตอนนี้ประมาณ292คนเนาะทางที่ออนไลน์นะครับที่ไม่ได้เข้ามาร่วมข้างในของจิสดาเราถามเป็นภาษาไทยก็ได้นะครับมีคำถามเกี่ยวกับเรื่องของการใช้ตัวแอปพลิเคชันของ L2 ภาพเกี่ยวกับเรื่องของซาหรือการใช้แอปพลิเคชันเมื่อกี้มีใครไม่ทันบ้างไหมครับผมจุดไหนหรือว่าอยากจะถามเรื่องของการประยุกต์ใช้งานภาพซาในเรื่องของเกษตรในเรื่องของน้ำเรื่องของป่าไม้เรื่องของต่างๆได้ถามได้นะครับ
ขอสอบถามนะคะฮัลโหลได้ยินไหมคะฮัลโหล
ครับเชิญเลยครับผม
ค่ะพอดีจะสอบถามว่าระบบของ Google ตัวเนี้ยค่ะมันสามารถมาพัฒนา GIS ได้ไหมหรือว่าเป็น API อย่างอื่นที่จะมาทำหรือช่วยอะไรได้บ้างค่ะเพราะว่าพอดีกำลังจะคิดกำลังรวบรวมพัฒนาระบบ GIS อยู่
GNSS ใช่ไหมครับผม
GIS ค่ะ
GIS โอเค GIS ครับผม
API อะค่ะใช้ API อะไรของ Google นะคะในการช่วยในเรื่องของ GIS
they would like to know that you have any API of the Google Earth Engine in your web application to
There is no API at the moment, but maybe I take it as a suggestion. Maybe in future, if there is a good algorithm that we are confident about the accuracy, maybe we can work on that.
โอเคตอนนี้ยังไม่มีนะครับผมในอนาคตเขาอาจจะพัฒนาเพิ่มครับ and the platform of ALOS tool you recommend me the application of use this platform for like comparing the image from the past and the previous or the time comparing or another else you can you suggest me
Yeah, that would be also another potential. Thank you for bringing this up because once you mentioned, I thought that, okay, that could be also another application. So that would be a good source probably to visually compare before and after. But you need to note that there is no any way to export the result of map or image into your machine at the moment. Maybe in the future there is some potential, but that would be only based on visualization, or if you want to have the image, you can screenshot the display panel.
But the Pegasus, can we extract it by the CSV or some other results? So of course we cannot to provide in the image or raster data, but we can export it in the Excel file or something. That is one of the way to.
Yeah, I take that as a future task.
ขอสอบถามเพิ่มเติมนะคะ ในแพ็กเกจของตัว Google Earth ตัวเนี้ย Engine ตัวเนี้ยมันเป็นแพ็กเกจที่ต้องเสียค่าใช้จ่ายใช่ไหมครับ
that is free or we have to pay some charge for
No, completely free. Yeah.
completely free ครับผม free
After this session, we have another session that we work with the people in this room, and we open up the code, and also the code for the application would be accessible for all the people. So we hope that we work together to improve the algorithm itself. So that's why everything would be free, the code, the image.
Okay, another question is that how the ALOS tool can detect deeply into the water?
Deep into the water?
Yeah, how deep to detect under the water?
I would refer this question to Sobue-san. Sobue-san, please, if there is a...
Yeah. There are no way to, unfortunately, there are no way to penetrate the water itself by the radio elements. So there are 0% to penetrating the water. But in the soil moisture content on the ground, we expect it can be done with several 20 centimeter or something. Therefore, we can estimating soil moisture, but not to in the water, ocean.
ถ้า detect ALOS 2จะ detect พื้นผิวของน้ำนะครับผมครับไม่ได้ลงลึกลงไปในน้ำนะครับ detect น้ำในนาข้าวอะไรอย่างเงี้ยครับได้อยู่ครับใช้ L-band
ขออนุญาตถามนะคะ
Please give us a minute. We have one question from inside the room. We take that question and we come back to your question.
Okay, he asking about the land subsidence. In this application, can detect the land subsidence, or we need to process more?
Unfortunately, there is no chance for land subsidence because the data level is not compatible for land subsidence studies, and also Google Earth Engine structure does not allow the such kind of analysis. So if it's the land subsidence application, other level of the data and outside of the Google Earth Engine, unfortunately not possible.
But for using in the free of the software, like a European Space Agency providing SNAP with the free data of the ALOS to level 1.1 data, we can you can to producing in the subsidence information, but it's a more technical one, so it might be not easy like a Google Earth Engine. And the Google people know the importance of how to providing the subsidence or interferometric data, but they have the very big challenge to if they would like supporting in such kind of the data and interferometric on the Google Earth engine, as Pegam-san mentioned. Therefore, if you would like to have the subsidence, you have to definitely handling in the original level 1.1 data with the freely available some of the software like a Snap.
Okay, in the program, someone would like to know that ascending and descending, what's the different about this? Ascending and different, yeah.
I would refer also to Sobo-san to explain because I guess
Okay.
there is no person better than
Right,
Sobo-san
okay.
to discuss on this. Yes.
Yeah, because in the most of the data is right looking of the data. Therefore, ascending and descending can be seen in the different angles from the south, east or west. Therefore, if there are very high mountain, it's like an effect on the mountain. If you can see in the right looking from the east side or west side, it might be a difference in that you can see by the sun because of the Nadia looking. Therefore, we have to careful to using if you would like to monitor in the mountain area, you have to very careful to choosing in the ascending or descending because the result should be different.
Do we have some time to ask more question?
As long, yeah, I guess if the Sobo-san, there is no other commitment, can we continue for the Q&A session?
If there are no, I mean, I don't have any problem to continue if there are still questions. I'm happy to answer.
Right.
Until
So
P3.
So that can the SAR image can penetrate the land or the soil under the soil? How deep is it?
Yes, it's like a 20 cents or 30 centimeters. We can penetrate by the L band, but it's only the L band or the L. If you direct using the X band or C band, it's only penetrating several centimeters, like a 3 or 4 centimeters.
3-4 เซนติเมตรนะครับผม
So L2 is 20 centimeters. E6.
Does any special use this application for the disaster management?
Sobo-san, is there any
Yeah,
comment?
yeah. So there are several disasters we can supporting, including the flood and also the volcano eruption and the earthquake. So there are a lot of the application we can using this SAR image, and especially for the Thai flood monitoring is one of the important monitoring by using the radar because it's a cloudy condition or rainy condition. The radar is very powerful to penetrate and to know the inundated area by using the satellite. And also another thing in Thai is in the oil spill in the ocean. I know that some of the ship crash in the summit or some area in Thai before. So oil spill monitoring is one of the powerful tool by the radar.
아, ขอสอบถามเพิ่มเติมนะคะตัว Google Earth ตัวเนี้ยค่ะ มันมีชั้นเลเวลในการจัดการบริหารจัดการค่ะเหมือนควอนตัมไหมคะควอนตัม QGIS เนี่ยค่ะ มันขนาดนั้นไหมคะ หรือว่ามันไม่ถึงขนาดนั้น
QGIS
ใช่ค่ะ Quantum GIS ค่ะ ก็คือ Quantum GIS มันจะเป็นชั้นเลเยอร์ของ การเรียงระดับชั้น เช่นน้ำหนึ่งชั้นพื้นที่หนึ่งชั้นดินหนึ่งชั้นอะไรอย่างเงี้ยแล้วก็จะมีเลเยอร์ของเสาไฟฟ้ามีเลเยอร์ของบ้านเขตบ้านอะไรอย่างเงี้ยค่ะหนึ่งชั้นอย่างเงี้ยมันสามารถทำได้ถึงขนาดนั้นไหมหรือว่ายังไง
ครับผม In the platform, do you have any layer like a layer of water, road, home, or something like that can adding into this platform? Yeah.
That is part of the future plan. At the moment, there is no other ancillary data into the application, but to improve the error from the train, the effect of slope, in the next version, probably we would add some elevation data sets. And also, if there is any comment, we would be happy to take that and bring those data also into. But at the moment, no ancillary data, but there in the future, there is chance to be.
ครับตอนนี้ยังไม่มีนะครับเดี๋ยวอนาคตทางแจ็กซ่าอาจจะพัฒนาเพิ่มให้มีครับผม
But Pegasus, the road data is the general information is also the one of the layer in the Google Earth engine or the OpenStreetMap. So that we can to overlay the OpenStreetMap with the road information on our list. So it can be easy to turn on the Google Earth engine. Of course, in the detail of the road information or other information is not available, but we have to figure out what way.
Sure. For the next step, we will try to integrate OpenStreetMap roadmap data into it.
Someone would like to know that this can we detect the green area of the in the area of the province and specify into the ampere or narrow that to specific area across the country. Can we do that with this platform?
I afraid I couldn't understand the question quite clear.
They would like to know the green area and they would like to get more detail like a scoping the first scoping is for the province area and more into ampere district area and something like that in this platform.
So basically, the good point about Google Earth Engine is that it's always this ability to play around with the scale. So if you zoom in, you can increase the level of the visibility, and you can focus on district level. But well, the accuracy is always we need to consider how it would be accurate or not.
ถ้าลงละเอียดลงไปในระดับตำบลอำเภออาจจะไม่ค่อยละเอียดนะครับภาพครับผมแต่ก็สามารถที่จะซูมเข้าไปได้นะครับshould be the last question the last question is that can we detect the plant shortage of water of the plant with this platform or not?
Paddy?
The plant shortage water of the plant like when the plant or the tree have a shortage water situation.
So the question is about the shortage of water in the plantation, right?
Yeah, I think so. I think it should be this question. I think.
So I would refer the question to Sobus, and at the moment I cannot answer within the capacity of the application, but for the capacity of L-band SAR, Sobus-san, is there any capacity for L-band SAR to detect water shortage for the specific plantations? If it's the question.
Actually, I could not understand the detail of the meaning. So what is the meaning of the shortage of the water in the plantation area? But as I already mentioned, we can detect in the soil moisture on the 20 centimeter in the skin surface. Therefore, when we detecting in the soil moisture on the ground, you can know the whether or not it's very dry condition or enough water. So that is a way to understand in the water content in the soils. On the other hand, if he or she would like to know in the like a water level in the paddy field, we are just going to the testing in the water level measurement by the relevant surf. That is the current condition.
ครับผมก็คือสามารถที่จะถ้าเป็นเรื่องของการขาดแคลนน้ำของพืชก็ตัวเอลอส2ก็จะดีเทคเรื่องของความชื้นของดินนะครับ25 เซนติเมตรนะครับผมประมาณนั้นครับครับด้วย L band นะครับครับผมก็เซสชันนี้เราน่าจะจบกันไว้ตรงนี้ก่อนเนาะแล้วก็เดี๋ยวถ้ายังไงเดี๋ยวผมจะประสานงานทางแจ็กซ่าทาง Restec อีกทีหนึ่งในอนาคตในเรื่องของการอบรมผู้เข้าร่วมออนไลน์นะครับให้มีความละเอียดลึกขึ้นกว่านี้นะครับครับผมยังไงฝากทางผู้เข้าร่วมประชุมทางออนไลน์ได้โปรดให้คอมเมนต์ผ่านตัว QR code บนหน้าจอตอนนี้ได้ไหมครับผมเพื่อทั้งเราจะได้เอาไปปรับปรุงในอนาคตครับขอบคุณครับผม
Should I scan the QR code? Hello?
Thank you very much. And to finishing today.
Thank you, Sobo-san. We take all the questions and from here we close the session, and after a break inside room we will continue with another part. I would like to thank you all the online participant and those people who join us in the room, and we are really grateful of the GISTA support. They really support us for the interpretation and all the preparation, and thank you so much. With that, I would like to close the meeting. Wish you great day ahead, and hope to see you somewhere else again. Thank you.
See you next time. Bye bye.
Wait. I'm not quite sure that can we take a picture online picture. I'm not quite sure.
Yeah, it's good way. I look mine.
So in that case, I would like to ask everybody in the Zoom if it's possible, turn on your camera.
If possible.
If it's possible, please turn on your camera. We will have you on the screen and we take a group photo.
Somebody take
a screenshot, or should I take a screenshot from? Okay.
Okay. That's right.
There is an option that you can only visualize, bring those who turn on their
ขอบคุณ
camera.
มากครับ
Let
ผ
me
ม
see.
ถ้าใครเปิดกล้องได้รบกวนด้วยนะครับ
You're coming?
เดี๋ยวโอกาสหน้า
Let's wait.
ถ้าทางบ้านถ้าเป็นออนไลน์เดี๋ยวทางจิสด้าเราจะประสานงานไปต่อนะครับถ้าเกิดว่าเรามีงานอีเวนต์อะไรหรือว่าเรื่องของการอบรมนะครับเดี๋ยวทางจิสด้าเราจะติดต่อไปเรื่อยๆครับ Is that okay? พัทรพล can you capture the picture? Okay, now it's okay. ขอบคุณมากๆเลยครับผมสำหรับวันนี้ครับครับผมขอบคุณครับ
Thank you so much. Have a great day.
Thank you.
Bye.
You have a great day. Bye-bye.
全員取れてますね。コロコロ変わってて、ワイナリー we can see. All